In this video, we're going to discuss the difference between two means when the data are not paired, unlike our previous video where we looked at paired data. This is our overview slide, which we'll spend about 5 minutes or less going over. Actually, it'll be pretty quick before we go over the main topics in more detail and with examples. Here, we are going to be looking at difference of two means for data that is not paired. In our previous video, we looked at paired data, and the example was the cost of books. So we would have a single book, but the paired data would be the price of the book on Amazon versus the price at the campus bookstore. So those data would be paired because it would be for the same book. Here, our data is not paired. The process will be almost identical to the one mean procedure because essentially the difference between the two means is going to give us one value, right? You subtract one value from the other and see if it's equal to 0 or some other number. But in this case, we're going to have a mean difference. And then the only difference is we're going to have a new standard error formula. We'll be using the t-distribution for inference when working with the standardized difference of two means if one, independence extended is met, and that is the data is independent within and between the two groups. Example, the data come from independent random samples or from a randomized experiment, and two, normality. And we can check the outliers rule of thumb for each group separately for normality. And then we will have this new standard error formula. Since there are two groups, we need a standard error that takes into account the two groups. So it's the standard deviation for the first group squared over the number of samples in the first group, plus the standard deviation for the second group squared over the number of samples in the second group. We also have the degrees of freedom, since we're using the t-distribution, is the smaller of n1 minus 1 and n2 minus 1. We will be doing confidence interval and hypothesis testing, and this is one of our main examples we'll go over in just a minute. So that completes our overview, and we're going to start right in with an example. I have our notes for confidence interval. When we can use the t-distribution, we need to check for independence extended and normality. And our example is, does treatment using embryonic stem cells, or ESCs, embryonic stem cells, help improve heart function following a heart attack? The summary statistics down below are for an experiment to test ESCs in sheep that have had a heart attack. Each sheep was randomly assigned to the ESC or control group, and the change in the heart's pumping capacity was measured in the study. A positive value corresponds to increased pumping capacity, which generally suggests a stronger recovery. Our goal will be to identify a 95% confidence interval for the effect of ESCs in heart pumping capacity relative to the control group. And just looking really quickly at our data, our sample sizes both have a sample size of 9, which is a small sample. Remember, our cutoff for not a small sample would be 30. Here, on average, our embryonic stem cell pumping capacity is a positive 3.5, so that's improved, a stronger recovery. And control is a negative 4.33, so it sure does look like there's a difference, but we want to know, is that difference maybe just because of an unfortunate sample versus something that we really would expect. And then our standard deviation for our sample of 9 is 5.17, and over here for the control group, also a sample of 9 is 2.76. And I also have these histograms so we can come and look and see if it's appropriate to use the t-distribution. So first, we need independence extended. So are the data independent within and between the two groups? Well, first, we are told that the sheep are randomly assigned to the two groups. And so, yes, we do have independence. And then second, looking at normality, so we want to see if there's large outliers. And here, we can see there's no large outliers. There are gaps, but it's not like there's a single point off by itself. This is a little cluster of points. And here's another cluster of sheep, I guess. And so in this case, these would not be considered outliers. And here, everything looks very clumped together. So definitely no outliers there. So yes, while there is variability and even holes in the histogram, there are no extreme outliers. I cleared out that work here to verify we can use the t-distribution, and I moved my table here to give us some more space. So the next thing we want to look at is what is the difference between the two means? So the difference in pumping capacity, so the mean of the ESC group minus the mean of the control group. So the mean of the ESC group is 3.5 minus the negative mean of the control group. So that gives us a difference of 7.83 units of pumping. And because it's an easy thing to do, the next thing I'm going to do is calculate the standard error and the degrees of freedom. So standard error, I'm going to take my first standard deviation squared over n. So here's 5.17 squared over 9. And then my second standard deviation, 2.76 squared, also over 9, and then square rooted, I get 1.95. My degrees of freedom, well, n1 and n2 are equal, so it's just going to be 9 minus 1 is equal to 8. Now I'm going to look at our t-score distribution table. If I want a 95% confidence interval, that means around the mean, centered around the mean, I want 95% of my data. That means outside of this confidence interval, I have 100 minus 95, 5% of my data. I split it between the two tails. That's 2.5 above our confidence interval and 2.5% below our confidence interval. So now looking at this, if it's one tail, I said we wanted 0.25 or 2.5%. For two tails, we want 0.05 or 5%. So here, and where did I have my degrees of freedom? Well, degrees of freedom was 8. You'll have to take my word for it, but in a minute you can verify. So what we have now is a t-score of 2.31. I've moved that up here. My test statistic for 8 degrees of freedom is going to be 2.31, meaning my 95% confidence interval is the difference in my mean, my 7.83, plus or minus my 1.95 standard error times my test statistic, 2.31. Sorry, often these two are swapped in my formula, so I really should have written 2.31 times 1.95, but it's the same thing. So my interval is going to be 3.32 to 12.34. So we're 95% confident the ASC improved heart's pumping by 3.32% to 12.34%. Our next example is from hypothesis testing. I left this here even though we've already determined we can use a t-distribution, but I guess the standard error formula is useful. And the example is here. Is there convincing evidence that newborns born from mothers who smoke have a different average birth weight than newborns from mothers who don't smoke? The data set below, over here, represents a random sample of 150 cases of mothers and their newborns. We are interested in two variables, weight, which represents the weight of the newborns, and smoke, which says which mothers smoked during pregnancy. We can see from the table that the mean weight of newborns from mothers who smoked was 6.78 pounds. For those who didn't smoke was 7.18. So it looks like that on average, if the mother doesn't smoke, you have a higher birth weight, which I think is supposed to be good. Then we have the standard deviations for the smokers versus non-smokers, and then the sample size is 50 versus 100. We have the histogram here, so we can go and see if we can use the t-distribution. We're going to check independence and normality. So first, the conditions. Can we use the t-distribution? Oh, that's why I left these notes up here. Okay. Conditions, well, it says that we have data sets represent a random sample of 150 cases of mothers and their newborns. So yes, data is drawn from a simple random sample. Observations are independent both between and within samples. Normality, looking at this, again, here, this looks pretty smooth. Here also, we have a gap, but that's okay. Both data sets are over 30 observations, so that's another thing. So variability in the histograms, even a whole bit here, but no extreme outliers. I did do this calculation of mean plus or minus 3 standard deviations for the non-smoker. I'm going to let you do smoker yourself, but the mean is 7.18 plus 3 times the standard deviation, 1.6, which is equal to 7.8 plus or minus, this would be 4.8. So that gives us a range between 2.38 and 11.98 So looking at our chart, again, I did non-smokers. So 2.38, that's over here. So we do have a little bit beyond 3 standard deviations, but remember, because we're in a t-distribution, like that would be really unusual and more of an outlier for the normal curve. But for the t-distribution, remember there's a little more spread in the t-distribution, and also the degrees of freedom. Actually, this is pretty big degrees of freedom, so we're really approximating normal. Usually for normal, we would look within 3 standard deviations to determine if there are outliers. Here, the book decided to stretch this one a little bit. The 2.38, everything above 2 is good. But the lower, this might be considered an outlier, but your book said it wasn't significant enough. And we're going to do hypothesis testing. So our H0 is there's no difference in weight. So our mean for the non-smoking minus the mean for the smokers is equal to 0. And our alternative hypothesis is there is a weight difference. In other words, the difference between the two is not equal to 0. Doing some of the quick, easy calculation, the difference in birth weight from our sample is going to be 7.18 minus 6.78. So that's 0.4 pounds. So there certainly is a difference, but is that just due to sampling because we happen to get the right sample, or is this a real difference? Now we calculate standard error, which is our standard deviation for our first group squared over n sample size for our first group. So we have, where's our standard error? 143 squared over 50 plus 160 squared over 100. And then we square root the whole thing and we get 0.26. Degrees of freedom is 50, the minimum of 50 minus 1 and 100 minus 1. So this is what, 49 and 99. So the minimum, the smaller number between 49 and 99 is 49. Also, we're going to use a significance level of 5% or 0.05. And so the next thing we need to do is calculate a t-score, or our test statistic. So our t-score is going to be our difference between our sample, which is 0.4, and our hypothesis, our H0. So 0.4 minus 0 divided by our standard error, 0.026. So that means our t-score for this 0.4 measurement we got in our, where is our 0.4 measurement? Here, that we got in our sample, and let me just underline that so I can find it, is 1.54 standard errors above our H0. Put a different way, so H0, we're going to assume H0 is true, and the real difference between the populations is equal to 0. Our sample, which was 0.4 difference, is 1.54 standard errors above what we were expecting with the null hypothesis. My table I have on paper doesn't go to 49, so I looked it up. So degrees, using the internet. So using degrees of freedom equals 49, and t, our test statistic, equals 1.54. For one tail area, I get 0.65. Since my hypothesis testing is about equaling 0, that means I want both tails. I want the possibility that the mean of the non-smokers minus the mean of the smokers is less than 0, and the mean of the non-smokers minus the mean of the smokers is greater than 0. In other words, for HA, right, because it's not equal to 0, we need both of that this is greater than 0 or less than 0. So I want both tails, so I double the area to get a p-value of 0.135 or 13.5%. Again, I doubled the one tail area of 0.065 to get 0.135 or 13.5%. So my p-value is 13.5%, which is greater than my alpha, my significance of 5%. So I do not reject H0. In other words, if H0 is correct and there's really no difference, I can expect a value something like 1.54 standard errors above H0 13.5% of the time. And that's not bad. So I don't want to reject it. It's not something weird. You know, something happening a little more than 10% of the time, it's unusual, but it's not totally weird. So there's not sufficient evidence to say there's a difference in birth weight. So your book points out that we've seen so much research suggesting smoking is harmful, so how could we fail to reject the null hypothesis, and what could we have done differently? First, if we made an error, it's a type 2 error. So of course we could kind of change our significance level so that we don't get as many type 2 errors. We could also use a bigger data set, and it does turn out that in bigger data sets, often most research will find there is a difference in the birth rates. One more example of hypothesis testing. An instructor has two variations of the same exam. Prior to passing out the exam, she shuffles the exams together to ensure that each student receives a random version. She would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. We want to perform hypothesis testing with a significance value of 0.01. So here we have our sample, what happened. We have version A, version B. There are 30 people who took version A, 27 who took version B. The mean score on version A was 79.4. The mean score on version B is 74.1. So certainly if you got version B, you might complain that maybe version A was easier. And that's the point of our hypothesis testing. Standard deviation is 14 for A, 20 for B. The min and max scores for version A is 45 and 100. The min and max scores for B is 32 to 100. First, we want to determine if we can use the t-distribution. And the first condition of independence is met because she shuffled those exams, which gives us random assignment of exams. We assume she shuffled them and then gave them out randomly. So normality, no extreme outliers. Scores for each exam were within 2.5 standard deviations, unlike our last example, so this is kind of nice. So I calculated the z-score for version B. I don't know why I did version B first, but I did. So for the minimum score of 32, I wanted to know how many standard errors it was lower than the mean. So I took 32 minus the mean, 74.1, divided by the standard deviation, and I get minus 2.1. So even the lowest score is well within 2.5 standard deviations of the mean. I did the same for the max, and I saw that its z-score was 1.2. So all scores for version B are within 2.5 standard deviations. And for version A, I'm sorry, that looks like a 4, but it's an A. I did the same thing. I took the minimum, subtracted the mean, divide by standard deviation, I get minus 2.45. And then I did the maximum minus the mean, divided by standard deviation, and I get 1.47. So all scores, again, within 2.5 standard deviations. So both independence and normality check out. And we can use the t-distribution. For hypothesis testing, we're going to write our hypothesis, and H0, as always, there's no difference between the two means. So no difference in test scores. That is, the mean of test A minus the mean of test B is equal to 0, and HA is always going to be there's a difference. In other words, the mean in A minus mean in B is not equal to 0. Next, I'm going to calculate everything that's easy. First, the difference in the mean. So the difference between the mean of test A and test B. So we have 79.4 minus 74.1, and we get 5.3 points. Next, standard error. So I take the standard deviation squared over sample size, 30, plus our standard deviation over here, 20 squared over our sample size, 27, and I get 4.62. The degrees of freedom is the minimum of our sample size of 30 minus 1 and 27 minus 1, so this is 29 and 26, so 26 is our degrees of freedom. And finally, my t-score. So I take the difference of the means, 5.3, subtract it from what we had predicted with H0, which is 0, and then divide by the standard errors, 4.62, which is 1.15. So here's my table. I'm at degrees of freedom of 26, so I'm going to underline this line. I can see I have t-scores. They're starting out at 2.78, they're going down, and the smallest I get is 1.31. I actually want to get even a little bit smaller than that. I want 1.15. It's not on my table, but one thing I can notice, as my t-scores go down, my areas for the one tail goes up. Right here it's 0.005, and finally, as I'm decreasing in t-score, you can see my one tail goes up all the way up to 0.1 over here. So that means my t-score, as I continue to go down from 1.31 to 1.15, I expect my area for the one tail is going to be greater than 0.1. So that's what I've noted here. My table does not go lower than t equals 1.31 for degrees of freedom equals 26. But at t equals 1.31 is one tail is 0.01. So at t equals 1.15, I should have even more area than 0.1. And we're going to use 0.13 because that's what your book uses. So I unenlarge this here to make some space. So for t equals 1.15, my t-score, and degrees of freedom equals 26, I'm going to use the one tail area of 0.13. Because we want two tails, right, because our hypothesis testing is that it's not equal, so we don't want to just take into account here one tail, that it's greater than or less than. We want that it's greater than or less than. We need to double this 0.13 to get 0.26 or 26%. That means our p-value is of alpha, which is 0.26, is greater than, did they tell us what alpha to use? Significance level 0.01, right? We're all the way up to 0.26. So we're not going to reject the null hypothesis. The data does not support any real difference in grades. To review what we've covered, we looked at looking at difference between two means when data is not paired. Our t-distribution can be used when we have extended independence and normality. We did confidence intervals, and we did a hypothesis. We actually did at least two, maybe three hypothesis testing examples. So that's it for this video. Thank you for watching.